posto. Eh,
Hello, everyone. I'll stand one more step. So this is, welcome everyone back for the first session of this afternoon. I'm very, very happy to introduce Omiros Papaspiliopoulos, who needs no introduction, but in case he's a well-known researcher working on methodology for MCMC and theory for MCMC, as well as stochastic models. He's won a lot of awards. And if you want to learn all of them, I encourage you to go to his webpage. But more importantly, he produces olive oil, which he exports. This is quite an achievement.
At least I produce something.
Yeah, exactly, yeah. On top of papers. So he's going to talk about large-scale inference for mixed models, and the floor is yours.
Okay, thank you, Judith. Before I start, let me just tell you that at the very end of my talk, there is an important announcement. So if for no other good reason, just stay until the end. If I tell you what the announcement is, I'll spoil, there's an important one anyway. So thanks for the invitation and for the introduction, Judith. I'm going to talk about some of the work I've been doing the last 3-4 years. Actually, it is a topic that I entered through commercial activities. So I started being interested in this from a commercial point of view, due to activities I do in terms of more entrepreneurial stuff. So it really meant to be very practical, because the reason why I got into it was very practical, actually. So it's primarily work with two colleagues of mine. Sometimes there are also other people involved, of course, but primarily with two collaborators. One is an outstanding statistician, Giacomo Zanella, who is actually giving also a talk right after this session. By the way, I should advertise that we have this Biometrica session, which is in the next slot. So he's going to give a talk there about something else, actually. And the other is an outstanding political scientist, Max Koplerud. And as I said, everything I do here, I would like this to become very practically, let's say, accessible. There is a software which is implementing everything you will see today. It's in R. Its current title is VG-LMER, and it's available on GitHub. You can find this. But the title might change in the next year. And then what I'm going to present here is also part of a fairly advanced book, which is forthcoming with Max. And it's with Cameron Hall on the Green series. Okay? So this is the plan of the talk. So let me just get down to it right away. The framework, I think it is probably the most fundamental statistical framework for applied statistics. Let's call it generalized bilinear mixed models. So in terms of the structure, there are three main components here. One, so basically there is, you model data Y through some bilinear predictor, eta, in the usual generalized linear model way. And then this bilinear predictor is made by three things. The third is what makes it bilinear. The first two make it linear. So there are what we can call typically fixed effects. So there are continuous covariates associated with every observation, X, with parameters beta. And then there are many categorical factors. Okay? I'll give you two concrete examples in a second. And associated to each categorical factor K in this notation, there are random effects. For every level of every categorical factor, there are random effects associated to it. Okay? But then we also allow for a bilinear term, which involves multiplicative interaction between random effects. Okay? So in terms of the defining characteristics of this structure, which think of it also as a module for building software out of that, there are continuous covariates. Okay? There are categorical covariates with additive interaction random effects. So there is the enter in an additive way here. And then there are associated to each of these observation I, there are continuous covariates X, there are categorical covariates Z, K, for K of them. And then there is a design matrix Z associated with a pair of interactions. And then you have multiplicative interaction between the associated random effects, okay? And all the random effects here, additive or multiplicative, they are assigned Gaussian distributions with sparse precision matrices. So the defining characteristics is the equation on the top, the fact that typically this vector of categorical covariates for every observation and this design matrix associated with the pairwise interactions, they are sparse matrices or sparse vectors. And then the Gaussian priors are all sparse, diagonal or of this kind. Okay, so that actually incorporates as special cases pretty much the majority of basic statistical models used in applications. So generalized linear mixed models with random intercepts, random slopes, and multi-way, I will refer to a term coined by Andrew Gell-Mann, deep interactions later on. But of course, also generalized additive models is a special case. These two categories of models are like additive interaction only. And then there are models with multiplicative interaction. Typically, they're not written adding any additive terms at all, such as what is called typically item response theory or factor analysis, depends on the literature you're looking at, or also probabilistic matrix factorization, which is, again, a variation of the same idea from a different literature. And then there are actually also the same machinery is used for modeling network data. And typically there, you have additive and multiplicative terms, okay? Now, let me just say something here that actually, the last term, it's very closely related to the second term in the sense that effectively what you can think of multiplicative interaction as a low-rank version of a two-way additive interaction, okay? So when you have two categorical factors and you want them to interact, and they are very big, so that basically full interaction doesn't make a lot of sense. Effectively, the multiplicative interaction is a statistically sensible way to encode that low-rank additive interaction. Okay. Right. So there are two motivating applications that I'm going to highlight some of the results. So the first one is the framework of what is called deep MRP. Actually, Andrew Gell-Mann talked about that. Of course, he relates a lot with his work. So this is basically MRP stands for multi-level regression and post-stratification. It's a very canonical way to do small area estimation. Okay, it's a really neat way to do this. And effectively, this class of models are typically of the generalized linear mixed models. They only involve additive interactions, but they are multi-way interactions. So here is I'm actually going to use a data set which has been used a number of times. Also, we have used it a couple of times in our own works. Originates from this work here. And in this, what I'm going to show you later, we're going to consider models of increasing complexity. And here, increasing complexity means deeper and deeper interactions between categorical factors. So here, basically, there are some fundamental categorical factors. So in this application, what the output is your intention to vote. By the way, both of my examples have to do with elections, and they are very timely the day after the 4th of July. So the ones about, this first application is about data from post-election surveys, try to understand whether people were likely to go to vote or not, depending on different things, and to predict voter turnout, which is one of the most fundamental things in predicting electoral behavior, okay? Whether you are planning to vote next time. So basically here the response is 0 or 1 if you're planning to, if you went to vote, yes or no. And then you have many categorical factors to try to predict that, and then you post-stratify to create small area estimation of these things, which then you feed them into a machine that gives you voter prediction localized across the country. So here the categorical predictors, some of them are very fundamentals, like age, like demographics, age, ethnic group, income level. But then there is factors with more levels, like the state. So there are 51 states in the United States, so which state in the country you live in. And then you start building important two-way interactions between those, so state and age, or for instance, income and age, or region and age, etc., or even three-way interactions, okay? So as you move from left to right, you have models of increasing complexity, and complexity here means basically you have deeper and deeper interactions, and this reflects into the number of random effects involved in this model. So the most complex in this setting models, they involve about 4,000 random effects, okay? There are about 70,000 observations in this survey, okay? So that's one application. I'm going to show you some results, and I'm going to try to see how computational methods perform as you go to higher and higher dimensions here. The other application I'm going to discuss is something that relates to a project I'm involved in, directing in some ways. centered at the Institute of European Politics at Bocconi. So basically, we are monitoring the way the European Parliament votes. By the way, European Parliament is a really good place for big data. They are legislating like there's no tomorrow. They produce a huge number of votes, challenging really the capacity of the person to analyze the data, maybe on purpose, I don't know. So for instance, now the European Parliament 9, a typical data set of understanding voting behavior of the members of parliament. So this data is within the European Parliament to understand how different members of parliament vote and their ideology. This is a typical item response type theory analysis, and this business is called ideal points, okay? So for instance, in European Parliament 9, there's a data set of about 16 million. So the I in the previous slide runs from 1 to 16 million, and there are about 18,000 votes. Actually, the data set is so big that you cannot really read it in memory anymore, okay? So it's big data, even in these typical old school social science applications. So, and here basically our goal is to build, we're building actually an infrastructure which is scraping this data from different sources that European Union stores these parliamentary results. We have this thing where you can go and look at it, which you see basic summaries about how people have voted. And we are building a certain analysis on the basis of this data. Something analogous for those that are more familiar with the American system to vote view in the United States, okay? So I'm going to highlight, this is an example of the models we're going to try here are both additive and multiplicative interactions, okay? In particular here, the categorical factors is things like the country you're coming from, the political party you're coming from, but also your identity. For every different member of parliament, there will be a different level. It will be treated as a categorical factor. And also the bill you're voting for is also another categorical factor and it has different levels, actually as many as a few thousands of them, okay? Right, so what I'm interested in is what we can call large-scale inference, by which I mean, I'm interested to fit these models to situations where both N and P are very large, okay? And in fact, in these classes of problems, typically, as N gets larger, P gets larger as well, or the other way around. So typically, they are both large simultaneously, okay? You really try deeper interactions when you have bigger surveys. Or for instance, in the case of elections, you really have, the more votes you have, the bigger N is, the bigger the number of random effects are because you have more votes to vote for. So my goal here is to do approximate inference and be able to balance two different important priorities. One is, I want to do it at a cost, at an overall cost, which scales linearly with N and P, so that basically I can scale it up to very large problems, even problems of this type that I'm telling you, which are in some sense classic in many ways in social sciences, but they have become really large scale these days. The other priority I would like to balance is uncertainty quantification. So I would like to make sure that the approximations I will be doing in the inference, they're not going to get worse and worse as N and P get large. So I don't get poorer and poorer uncertainty quantification, because uncertainty quantification really matters in many of these problems, okay? So summarizing a little bit of what is the overall work we've been doing along these lines, we have what we can call provably scalable and accurate large-scale inference for generalized bilinear mixed models. Part of this agenda is already completed, and you can find articles I'm going to show you in the end. Part of it is being progressed these days. So we have a set of tools which are both computational and theoretical to both develop and analyze, so create algorithms and analyze their properties. For algorithms that they are typically used in this context, for instance, we have results for Markov chain Monte Carlo algorithms, either for what we can call exact inference, so basically there is Gibbs sampler type algorithms, or for approximate inference using conjugate gradient methods, etc., for approximate posterior inference. And we have also results for variational inference. I'm going to focus my talk today on that for concreteness, but there are analogs of what I'm going to say to all the other things. And in fact, the tools we have available, they're also relevant for algorithms that they're doing map estimations, and some, for example, things like alternating least squares or backfitting, or alternative methods for estimating hyperparameters in these models. For example, if you want to do restricted maximum likelihood or Birkal Bayes and stuff like that. So it's actually very generic. So the focus of my talk is going to be on what is typically called free-form variational inference. But there is analogs and synergies with all the other methods, in particular with MCMC, but also with other approaches, optimization approaches for map estimation. And There is one thing that VI, I think it's has an advantage here, apart from being, as I'm going to show you, provided you do it appropriately, it strikes a good balance between being fast and accurate. It has an additional advantage for multiplicative interaction models, is that you can impose, on the inference stage, you can impose structure on the multiplicative latent variables. So for example, you can impose what is called disentangled representations in variational autoencoders or in other literature from machine learning, which is basically, you can impose that, for example, the latent coordinates are independent, etc., which is actually useful. So it gives you a nice, coherent, and let's say, principled way to impose structure on slightly misspecified, slightly unidentified or fully unidentified things ex post. All right, so the next part of my talk, I'm going to describe the general methodology, what is the general idea, and give you some illustrations of the methods we have developed in these things. And these illustrations are also going to highlight some issues, both for the asserted quantification and for the accuracy, which the next part of my talk, which is on the theory we have developed to understand these methods on these models for large-scale inference. The theory then tries to explain or to predict or to give some insights and guarantees. So the first thing to say here is that when I started out the talk, I told you, there's the structure of the models. There are sparse design matrices. There are sparse precision matrices in the latent variables. There's a lot of sparsity here. And it matters. And actually, every single implementation we have on these things is taking advantage of that sparsity when there is there. Okay, so we work basically with sparse matrix vector multiplications and never do much more than that. However, that sparsity, and that's a key property of these models, which I think differentiate them fundamentally from many other areas of applied models in statistics, is that this sparsity is not one that looks like a very structured sparsity, which gives you block diagonal or banded or matrices that they're easily factorized. It is actually a very random type sparsity that it looks like the data that appear in a high-dimensional contingency table. And it turns out there is mathematical reasons that you can relate that unstructured sparsity to that resembles how random graphs look like. And that's a connection that you will see coming up later in the theory. And it is a problem, but is also a solution to the problem, provided you deal with it appropriately. So the sparsity here is one that it is not amenable to sparse linear algebra software that can deal with it successfully. And in fact, I'm going to show you some numerical illustration in the next slide, but in fact, you can prove for certain designs that sparse Chol, for instance, like doing sparse Cholesky, it has the worst type complexity, it has cubic complexity, okay? So you can actually prove it for certain random designs that will be the case. So we know that, and we have also extensive numerical evidence, and also extensive numerical evidence of trying to make very high quality and very optimized software like LME4 or INLA work when you really take dimensions to very large numbers. Eventually, you will see even these highly optimized pieces of software, which they are pretty good at doing the uncertainty quantification business. Eventually, they will have that polynomial complexity, okay? So this is just a quick illustration of this point. This is simulated data, but from designs that they are resembling designs you get from kind of survey data, for example. What you see here on the x-axis is the P, is the total number of random effects. This is generalized linear mixed model simulation, so there are additive interactions only in this plot. So here you have P in logarithmic scale, and what you have with red is the cost of doing sparse Chol on problems of increasing size, so basically doing the decompositions of the matrices that they come up in that calculations. And the slope that you see in these figures, this is basically the first two are with 2 factors. The last one is with 5 factors, 5 categorical factors. Pretty much in every situation, eventually these costs are cubic, okay? So the slopes here are 3. You can do more interesting things with approximate sparse linear algebra, like conjugate gradient, for example. And there is a talk later by Andrea Pandolfi, who have worked with together on this kind of stuff, and you can see more about that later, actually. But the message here is that sparsity matters, but it doesn't help. So that's not the way to go. So if you just look at the model structure, there is this additive predictor, and this additive predictor basically links each of these terms to the actual observation y. okay? So a priori, all of these terms here are independent. These models are super unstructured a priori, and they collaborate all together to give you predictions on the actual Ys. So what you have here is actually, in some very high level and, let's say, intuitive way, you have a version of a problem which I have thought about quite a lot in the past, and many other people, of course, which is this issue of non-centered constraints from the data. So you start with things which are a priori independent, and the data impose, let's say, dependence because of the existence of that linear combination that has to match the data. And in fact, what happens is that that non-centered constraint gets stronger and stronger as N and P both get large. So in the large-scale regime, this gets worse and worse. And this is something that you will have to be prepared that methods that you throw on these problems, they will eventually suffer from that unless you do something about that. And this is what I'm going to show you how to deal with. And you will see in the numerics later, in the theory as well, what happens when you don't deal with it. You pay the price. Interestingly, you pay the price both in terms of computational performance and in terms of uncertainty quantification. So we'll see this in next few minutes. Okay, so that non-centered, so what also makes this class of problems very distinct from other types of hierarchical models that are used commonly is that this non-centered constraint is not one that can be dealt with by centering, because you have several of these categorical factors. If you had just one, there would be a very neat solution. But once you have more than one, you cannot do that anymore. It doesn't work. And in fact, there is an article by Gareth Roberts and Giacomo, which look at different versions of parameterizations and why, for such problems, for instance, they're not really giving you any improvement. So to explain to you what we do first in terms of a generic methodology to solve, to obtain good performance in large-scale regime, let me just recall the notation a little bit. So basically, I have additive and multiplicative terms. Okay, so basically, I have, I'm going to call by theta the vector that contains the beta coefficients, what we call typically the fixed effects, and all the additive random effects. So this vector runs from 0 to k. There are capital K categorical factors. Maybe some of them are two-way or three-way interactions of more basic factors, okay, but I don't care about that. And U and V are going to denote the multiplicative effects. And then there's other terms, of course, in these models. There are variance hyperparameters, the variance components. All these random effects, they come with variance and covariance matrices because you might have also correlated random effects and stuff like that. There might be additional latent variables associated to every observation. For example, if you do polygamma augmentation or other types of augmentation or dealing with missing data or other things. So all of that stuff is going to be denoted by phi. And the interest, of course, here is to recover the conditional distribution of the unknowns given the data. So the fixed and the additive random effects, the multiplicative ones, and the hyperparameters. And we're doing here, as I said, I'm doing a fully Bayesian inference on all of the hyperparameters, but all of this machinery can be used to do other things if you wanted to, like empirical Bayes or restricted maximum likelihood or other things. Okay. So the key, so focus, as I said, is on VI, but there's analogs of these things to other modes of inference. So the key idea here is what we can call partially factorized VI. I have a slide, which I'm going to go very quickly. Well, actually, I'm not going to mention at all at this point, but you said, this reminds me of this, reminds me of that. Yes, it reminds you of many other things, but it's distinct from all of them for different reasons, which we can discuss. So the partially factorized VI, it works as follows. The idea is theta is a vector of all these fixed and random effects, okay, the additive ones. So I'm defining two sets of indices, C and U. And the variational family I will define, so variational inference consists of defining a family in which your approximation will live, and then finding the best member of that family to approximate the distribution of interest, the posterior in this case. So the family is structured as follows. There's a lot of products, so it looks like a mean field in many ways, but apart from one fundamental term, which is this first term here. So if this thing were not in this product, this would be a typical mean field variational approximation. You just write down a factorization of the joint density with low dimensional dependence in every block and independence across blocks. That's the standard mean field VI. But instead here, we write a conditional density of theta C given theta U. Okay? So this is actually partially factorized and factorized. And all the terms in U, all the indices which belong in this thing, they are multiplied out here. Okay? And then the multiplicative ones are also multiplied, and phi is multiplied. So it looks everything like mean field, except for the fact that some of the terms, they are conditioned upon here instead of being just ignored. Okay? So there is two special cases of this framework that they are a little familiar, actually quite familiar. One is when the C is the empty set, so you don't put anything here, so the whole thing is missing. And if that thing is missing, we call this fully factorized VI. Effectively, because of the structure of the graphical model, then there is a lot of other factorizations which are implied by this. So you start with the basic factorization, but then the graphical model is such that all the terms that they are inside, all of these are multivariate densities, they all multiply across the terms, everything becomes independent, okay? So that is a very trivial thing to implement. It's very fast per iteration, and it's called FFVI from now on, okay? All right. Another extreme version of that, so that's the case where C is empty. The other is where C contains everything. So this is what we call it unfactorized VI. So unfactorized VI basically blocks together all the fixed and random effects. So in some sense, it can deal with the dependence between them quite nicely, but it comes at the cost that now you're exposed to order P matrix decompositions. I mean, you have a high-dimensional thing to work with. So there's no, like, the problem with UFVI is that you should expect that it should be quite good in uncertainty quantification. It might also require a very small number of iterations to convert when you try to estimate these things by computational methods I will discuss now. But you should expect this to be very expensive to run any iteration because effectively you have sparse Cholesky on these weird design matrices for which you have typically cubic complexities. So you're basically as bad as trying LME from the very beginning. Okay, let me just say that the idea that is mostly pretty much is the same idea in version of VI is partially collapsed Gibbs samplers, okay? So basically, this is the concept that is pretty much the analog of in MCMC of what this construct amounts to. So basically, just to wrap up, you define the variational family, you have a value function that you try to optimize this approximation with respect to, and this is the usual elbow, the evidence lower bound, relates to the KL divergence, to the reverse KL divergence. And then the optimal approximation Q star is the maximizer of that. So you try to make this as big as possible. As big as possible means you bring Q as close to pi as possible according to that value function. And Q star is going to denote that optimal. Now, by construction, and this is what basically in math, what I was saying earlier, just because of the way you've set up this family, every time you vote. So these are called ideal points. Effectively, they are the multiplicative random effects associated to every member of parliament. And if you are familiar with European politics and if you're familiar with this kind of analysis, it is well known. This is not something that comes from this plot here. I think this plot here does better than things that people do massively. It is well known that in European politics, in European Parliament, there is effectively, if you just look at the two latent dimensions for the multiplicative effect, the one picks up left-right, and the other picks up pro-anti-Europe. And you can see this in this data set exactly like that. So there is, this is the European, this is the party in the European Parliament that corresponds to the socialists. Okay, these are the liberals. This is the European Popular Party, that's a right-wing party. This is the Greens, and this is like left or some other even more extreme left parties in the European Parliament. So basically the left to right is really from left to right wing, and the north-south is pro-Europe, anti-Europe. So just here, to make this talk a little more entertaining for everyone, because some people clearly, some are more interested than others, as always, in these talks. So there are some circles, which most of the circles are filled, and some are empty. See, there are some circles that are empty, most of the others are filled in. What do you think the empty circles correspond to? Let's see. Who can guess? So some of these circles, they are empty. There's quite a lot of those here. And all the others are full. What do you think the empty circles correspond to? Say that louder. It is UK. Before Brexit, they used to be part of the European Parliament. But you could see them going out. Because you see, for example, here, this is the European Popular Party, the right wing, and these are the Tories. Can you guess which ones are those here? UKIP. You remember UKIP? Farage was elected also yesterday. So So you can see that this is basically, even within the European Popular Party, there is an obvious different behavior in terms of the Tories, which they are a little bit more to the center, but more to anti-Europe than everyone else. You can see this in the data. So these are the multiplicative terms, which give you basically some insight about voting ideology, if you like. But what is interesting is that in these models you have also the additive term, and here I'm plotting the additive effect versus each dimension of the multiplicative one. And you can see that effectively what the additive term can do here quite nicely is at first pick up anti-systemic behavior, because some people vote negatively no matter what the law is. It's not like because, so you can see, for instance, here a very strong negative term. The more negative, the more likely you are to vote no, according to the model. You see basically a very strong negative effect from the UKIP, for example, and other, this is I think Northern Ireland, if I remember correctly, members of parliament, okay. So this, and you can also see that the additive term here has a certain amount of correlation with the pro-anti-Europe, which is the second dimension. But you can see that's why these models are interesting for exploratory analysis, and this is why these models are important to be fitted in very fast, because you have to do a little bit of preliminary analysis before you make up your mind what to do later. You can see that, that this term, the additive term, correlates with the anti-systemic, anti-European behavior, but in a way which is very different from party to party. Okay, so you can see that for these parties there's a huge negative additive term, and this, but then you can see it's always the white dots, for example, the British members of parliament are always below their corresponding group, but in a way which changes from party to party. There is an interaction. Let me just say one last thing here and move on. That what is really cool about this machinery here is that because I can put several multiplicative interactions in the model, I can put on the same map both members of parliament and the country they come from in an ideological map. You can do all sorts of things like that. It's very nice construct and easy to do different things with it. Okay, so let me move on to the last fundamental part of my talk, which is the previous, okay, forgetting about the more entertaining part of the European politics, the previous part of my talk highlighted a few issues. One is that there is some duality between how accurate the VI is and how much time it takes you to find it. So I would like to understand this better, and I'm going to do it in the next few slides. And the other thing is that, of course, I would like to come up with methods which they come up with some guarantees that the accuracy and the computational performance is going to be good in large-scale regimes. So I can trust this and throw it out on large problems and feel in problems for which I cannot run MCMC to compare against. Okay, so if I don't have any theory, I cannot extrapolate beyond what I can check with other methods. And then there is another thing which is needed here, is to have a little bit more insight how to design the algorithm optimally. And among other optimality considerations is what to put inside that set C so that I get these good guarantees in the large-scale regime. Okay? So first, let me make a warning that you can, everything I'm going to show you from now on can be criticized in many ways. I can give you some criticism myself. But it serves all of these purposes. It does give you an understanding of this duality that you see in real data analysis. It does give you guarantees that you can see them in practice. And it does give you insights how to design the algorithm in a way that materially you see the impact. So it's a useful theory, I think, despite its obvious shortcomings as any theory. So the first thing I'm going to do is I'm going to define a measure of the accuracy of the variational approximation. And this definition of quality of accuracy of approximation, if you like, is going to be useful both for numerical purposes, but more importantly, it's going to be useful because as a theoretical construct, it really links quite nicely to the convergence in a way which gives you some very interpretable answers. So I'm going to define the so-called uncertainty quantification fraction. And the motivation for defining this starts from something which is a common perception among practitioners of variational inference, that variational inference is pretty good at locating modes of high-dimensional densities, but it is quite poor in capturing the variation around these modes. This is something that most people believe. I don't think it's exactly right, to be honest, but pretty much is, as a first-order statement is pretty reasonable. So what I'm going to do is to exactly focus on that aspect of VI, and I'm going to define this fraction, which is effectively comparing how much is the variance under your variation approximation Q of linear functions of your state vector theta, of your unknowns, relative to how much is that variance under pi. So how much basically your miss reporting variance of linear functions. And I'm going to basically define the direction where you have most of the uncertainty, misquantification, okay? So if you like, if green denotes your target, which is a bivariate Gaussian with some correlation, and red is your mean field variational approximation, which assumes that the components are independent, it's well known that the optimal mean field approximation is centered at exactly at the right mode. This is exactly the intuition that I was discussing earlier. What would be the vector V that optimizes the, well, if you like, the worst direction for uncertain quantification is the diagonal, is where you're doing most of the mistakes. So in that direction is where you are doing most of the errors. So this measure is basically, it has a PCA type interpretation. It gives you directions of bad uncertainty quantification, and this quantity is the worst of those. But if you can estimate this quantity from data, which is mixing simulation and your variational approximation, you can do a PCA type analysis and see in which directions you're really underestimating uncertainty. And that can help you redesign things later as well. So it's also practically useful, provided you can compute it in practice. And to compute it in practice, of course, you can only do it in problems for which you have access to MCMC that you can estimate effectively the denominator. But it's also useful for theoretical reasons, for reasons I'm going to show you later. Let me just say that you should not be too surprised, because this really looks like a PCA type of thing. And effectively, this quantity here relates to the maximum eigenvalue of the comparison between the covariance under pi and the covariance under q. Okay, so you look at the worst direction. Okay, so having defined this quantity, I can provide a theorem, and this theorem is under very strict assumptions, but it is a useful theorem. It gives you something interesting, which you can also contrast with the actual results. So this theorem, okay, so the part that you can, of course, criticize is that it's assuming that your target is Gaussian, okay, so which means that you have a convex problem, blah, 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 blah. Okay, I take all that. That's of course true, but that's the only theorem. Well, it is one theorem we can prove. You can prove a little bit more than that, but it gets harder. So the target is pi, is Gaussian, okay? The q theta is a partially factorized variational approximation. So effectively, you write down something like this. Forget about the multiplicative part here. You write down something like this, so you have a partial factorization, okay? And what the theorem says is it compares, it basically looks at how close to the optimal variational approximation I am after t steps, t iterations of Cavi. So I do t iterations of Cavi to find Q star, and I'm seeing how close to convergence am I. So I'm comparing effectively the value function at the optimum and the value function after t iterations of the algorithm. So I see how much I have basically reduced the gap. So how close to the optimum I am after t iterations, okay? So what this theorem says, to summarize these two statements here, is that the speed of convergence of Cavi is related to the uncertainty quantification fraction, both by an upper and by a lower bound. So if you like, if I just jump to a conclusion that comes out from this theorem, the conclusion that comes out from the theorem is that the number of Cavi iterations is like 1 over UQF. So whenever you have a bad quality of approximation, you have a slow algorithm. Wherever you have a good quality approximation, you have a fast algorithm. Fast by the number of iterations. It might be very expensive to do every iteration. That's a numerical linear algebra question. But in terms of how many iterations you have to run this for, which is a difficult question, the things do not work the way you might think. It's not that it is fast but inaccurate. It is fast and accurate, or it is slow and inaccurate. Which we saw actually in the deep interactions results I was saying earlier. Okay. But just a minor thing here, that it turns out that it's easier to analyze the convergence of a random scan version of Cavi, where you randomly pick one of the coordinates and you update it instead of doing it in systematic order, because that eliminates some arbitrariness, some dependence on the order, which is beyond the high-level understanding here. Okay. So the first conclusion from this theorem is that in order to basically, the first conclusion is that the number of iterations is like inversely proportional to the quality of approximation. So that's number one. The other message from this theorem is that in order to understand both the uncertainty quantification and the computational performance, you just have to study and control a single quantity, which is this UQF. So that's a really interesting possibility, because now I have one quantity, and by making sure that this quantity, as n and p get larger and larger, if this quantity is bound away from 0, so it doesn't get arbitrarily bad, I know that I'm going to have good performance computationally and good uncertainty quantification at the same time. All right, so basically, let me just, in the next 2 slides, show a couple of results that relate to that they stem from that observation, together with additional stuff, and then I will basically start wrapping up. So it turns out that we can build upon this theorem, and we can study a simplified version of this mixed model framework. It's a simplified, but still very powerful, that the conclusions you get out from this simple structure, they extrapolate quite well beyond it, so that makes it kind of interesting. So this is basically the case of just having random intercepts. So you have basically just a constant here, there's no x's, and then you just have the additive terms, and there's no random slopes or other things like that. So you can actually study, you can create theory. The theory will try to say things about UQF for mixed models in large-scale regimes. You can make theory under this structure, this specific case of the general framework, where you have k categorical factors, and basically gk denotes the number of levels in these factors. So some of these gk's will be very large if you're in these factors with many levels. And you can have either Gaussian or binomial likelihood. And here is basically 2 results I'm going to highlight among different ones we have. The first one shows that it's basically the mathematical proof that the FFVI, which we saw to be inaccurate and slow, it is like that. So you can actually prove that you have this kind of upper bound on the UQF, which effectively shows that in the large-scale regime where delta and the number of levels of at least some factors is large, this is basically going to 0. So there's no time, of course, to go into all the details of this formula, but the point here is that this result proves that UQF is getting worse and worse in the large-scale regime of the simple, fully factorized mean-field variational inference for mixed models, which we have seen in numerics, but this is a theorem that kind of makes that point. And similarly, we have a theorem which basically says that is a little more specific yet. It says that just for 2 factors, that's the most we can prove, and for basically under an additional assumption of the design, we can prove that the UQF of the partially factorized, that provided you put the fixed effects into the C set, so provided you put the fixed effects there, we have the result which implies that the UQF has exactly this specific form here. And what makes this form here fundamentally different from this form here is that there is this additional term here, which involves this quantity lambda aux. This is between 0 and 1, so it actually scales down all of these things. If this thing is small, that's good, because it means that the fraction is closer to 1. And this thing here is actually a measure of the connectivity of the co-occurrence matrix between factor 1 and factor 2. So that is what relates to random graphs, because as I told you, these co-occurrence matrices from this type of mixed model designs, they look very much like random graphs. So this lambda aux is a measure of connectivity, of how connected that co-occurrence matrix is. And we can leverage results from spectral graph theory to say things about that co-occurrence matrix in the large-scale regime. And it's actually quite well known that for random graphs are expanders. So as n and p get larger, they are more and more connected, which basically means that that thing here goes more and more close to 0, which means that the uncertainty quantification fraction goes more and more close to 1. So you actually have what we can call a blessing of dimensionality, where not only this fraction is bounded away from 0, but it actually gets better. So you have better uncertainty quantification and better performance as the dimensions get bigger. Okay, so it's an interesting result. And it's one which we have seen in simulations, etc. So I had some, okay, so in terms of the messages here is that this gives you an insight about how to set up C so that you increase the connectivity of that co-occurrence matrix. And I can answer questions about that if you want. But I had some further numerics that looks at this blessing of dimensionality and simulate data sets where you can play a bit more with this. And comparing with alternative implementations of VI, including fixed form VI, but I'll skip this for questions potentially. So at this point, I think it's a good point to stop. Here is the reference that corresponds to the material I presented. And thank you very much for your attention.
Any questions?
Thank you so much. This is just such an important problem, and speeding it up is so important, and I really, really loved your talk.
Thank you for that. We haven't agreed on this. Was not premeditated. It's a spontaneous comment. Yeah, go on, please.
But it's true, though. It's true, though.
Yeah, but we have never read before the person.
No. I also hate to come to the defense of mean field variational inference, and I'm definitely not going to come to the defense of CAVI. But I bet, and based on my experience, that if you were to use direct gradient descent or second-order methods to optimize the mean field approximation rather than doing CAVI, a lot of these problems with optimization would disappear.
Okay, this is a brilliant point. First, so I'm not going to go through it. I can talk also offline. We have numerics that they try Pathfinder, etc. But let me say this, there is categories of ideas that they can improve the convergence time, but not the approximation error. So doing something like what you said is not going to, because the approximation error depends on the structure of the graphical model. Sorry, yeah, but.
Okay, again, at the risk of shilling my own work, we have a paper on linear response covariance corrections, which can take in a good mean field approximation and pop out a covariance matrix. I'm not going to say it's going to work for here, but it's possible and at least worth checking. Okay,
of course I will check. That's obvious. Thanks for that.
Any?
Thank you for the lecture. My question relates to the random graph connections, which were mentioned only at the end related to spectra. Could this be extended any further? I mean, you connected to connectivity between factor-based random graphs, but you mentioned adjacency matrices and similar things. Could this analogy be extended and further? So
but extended in what direction? I'm not sure I understand.
You have multi-level models, so could anything of this be connected further to any type of?
Good point. It can, and some of what I'm saying here is kind of trying to make that kind of extrapolation. It's also bounded by my capacity to do random graph theory, so there's a limit to that as well. But I do think it's an interesting connection, and it's worth spending maybe a little bit of effort to try to do. So I have to tell you, however, that even some of these spectral graph theory results, they are under very specific random graphs. So actually, this is a reference from 2022. So some of these results they relate to Allen conjecture, and some of them are very hard to prove, even for completely abstract random graphs. So obviously, we are a little bit upper bounded about whatever is out there, because the chance of us proving something on that thing is completely insane. I mean, there are like people who work on that their whole career, and they make modest progress. So in a way, we are familiar with this literature, and we're trying to use what we can from there by making the right connections. But there are some conclusions that you can guess the right answer, and when you see it in the numerics, it's exactly like what you thought. So I can tell you more about that, actually. It's a good point.
David?
Thank you. It was very nice. So have you thought about, so in many practical applications, you might be interested in portraying the uncertainty, but not of any possible functional, because you're primarily interested in one or another, and then in that case, I wouldn't be interested in
that's exactly that.
Over lambda, whatever. So
no, but this is exactly that. So this basically says, this guy here says, this is the direction of the worst uncertainty quantification, which might involve some weird combination of random effects. This is basically saying, this is the prediction of voter turnout for every state, and you have 51 numbers there, and you have basically how accurate you are in each one of these 51 predictions, post-stratified. And then basically what you see here is that the fully factorized thing, immediately when the models they're really poor at that. And actually we know why also. So it's not it's an explainable reason. So the point I'm trying to make with this plot here is that for low-dimensional functionals that you really care about, this makes a big difference. It's not just that there are some directions that maybe they're not so important. Okay.
Okay.
And we have a number of other things actually that they saw that.
So before I give the word to somebody else, I ask a question.
Of course.
Two. So actually, I have two questions. One, you started your talk by saying that sparsity matters, but I haven't seen anything about sparsity in your talk, so I was a bit lost.
But you have.
Have I?
It was a little unsuccessful on my side, but you have, first, the one thing to mention here is that all of the implementations we have basically take advantage of sparsity. And for example, even in this European Parliament stuff, I only do sparse matrix vector multiplication. I wouldn't be able even to load the data as a matrix, okay? So all the implementation we have with the software, they really take advantage of sparsity. So the matrices are sparse. You cannot decompose them efficiently. So, but you can multiply them efficiently, and we do that. And the other thing is that this connection to random graphs builds upon that sparsity. Okay? So we say that, you know, especially for these deep survey designs, the coherence matrices you get are random graph-like, and then that gives us the connection to random graph theory. We have some conclusions that come from that theory, which when we implement on our framework, we see that they really give you the right idea about what's going, they predict the right behavior.
And so then I have my second question, which is, so you have a measure of accuracy of your approach.
Yes.
Does it give you something, does it tell you something about the accuracy on the elbow? For instance, if you wanted to do model choice, would that be useful?
But the elbow result is this one here. This basically says the rate at which you are, sorry, you mean the comparison between different families? Yes. We have in the article, we do in the article, so in one of the articles with Giacomo and Max, we do something that basically goes along this line. We say, you know, if you want to have elbow by that amount, how much time it takes to do different things, and so to some extent, yes. To some extent, yes.
Any other questions? Yeah.
Thank you. So I wanted to ask, with the UQF being so pivotal to the convergence rate and everything like this, is that to do with the linearity or the Gaussianity in the model? It's specific to this part?
Of course. This is assumption number one.
Okay.
So basically, by doing this random scan thing, I'm able to reduce the problem to a linear dynamical system, and for which I can then massage appropriately to get this sort of thing.
Okay. This doesn't apply to the GLMMs?
This is a complete generic theorem, provided that pi is just Gaussian with an arbitrary mean and arbitrary precision, okay?
Okay.
It has nothing to do with the specificities of anything else.
Sure.
What has to do with the GLMMs, or by linear models more generally, is that then I can tell you things about UQF. Mm-hmm. So this theorem tells me that UQF being large is good, both for uncertain quantification and for speed of convergence. Mm-hmm. And then I can tell you things about UQF for GLMMs. That's the two components of this theory.
Okay. Thank you.
Any other questions? Right, so let's,
yes,
oops, I'm missing someone.
No, thank you.
Yes,
but then I have to remind you that before we...
Yeah, you have an announcement to make. But so before the announcement and before you leave, let's thank Omiros.
So, please. No. It doesn't work, but okay, so I'm Kazu from Nagoya State University, Japan. This is an announcement of the next world meeting. I'm the chair of the local organizing committee, and yeah, the world meeting will be held in here, June 28th to July 3rd in 2026, and the venue is Winkaichi. This is very close to the Nagoya station, so you can easily come to the conference venue. And yeah, first of all, I think I have to explain where is Nagoya. Nagoya is located between Osaka and Tokyo, so the center of Japan, and this is the third biggest city in Japan. And you can easily come to Nagoya because if you have a direct flight to Kansai Airport or Narita Airport, then you can come to Nagoya by bullet train, and you also have a direct flight from Central Air. We call Central Air. It is in 30 minutes. And so this is very important for the students. So the accommodation is quite have a variety. So it's from $30 to $180 per night for single room. So it is good information for students to come to Nagoya and also senior researchers. So we are looking forward to seeing you again in Nagoya in 2006. So this is an announcement for the next World Meeting. Thank you very much.